Hello everybody, and welcome to Theorem 13.2. We are still looking at page 96 here, and we are about to prove a very interesting little theorem that relates integral domains and fields. Okay, let's read this together. Okay, it tells us simply that every finite integral domain is a field. Okay, maybe just to get some insight into how this relates to what we talked about before, let's look at the Venn diagram that we wrote a little while ago. Okay, so the Venn diagram tells us that every field is an integral domain. And so the Venn diagram suggests that there are integral domains that are not fields. This theorem says, though, that if the integral domain happens to be finite, have that additional property, it does have to be a field. It actually has to live in here in our Venn diagram. Okay, so let's see if we can prove that. This is kind of a nice little proof that we're about to write here. All right, so let's see, what do we want to assume here? We're going to start with a finite integral domain. Okay, and so since it's finite, we can give a number to the number of non-zero elements it has. So let's assume that it has n distinct non-zero elements. Okay, which means that we can write our ring kind of in this form. So there's a zero element, and then there's n things that are not zero, which we'll just call x1 through xn. Okay, and now the question is, what do we need to show? We'd like to show that this is a field. What properties does a field have to have again? Okay, well, let's scroll up and just remind ourselves. So it needs to be a commutative ring with unity. Now notice that we already have those two properties because we assume that R is an integral domain, and all integral domains have those properties. So really then, all we need to prove is the last part of the statement, that every non-zero element is a unit. All right? So that's going to be our strategy here. So we will take any non-zero A that lives in our ring R, and what we're going to show is that that has an inverse. Okay, that it's a unit, an inverse under multiplication. All right. So here's the first thing that we're going to do. This is kind of a strange step, okay, but it's going to end up leading us directly where we want to go here. Consider the set S that we get by taking all of the non-zero elements in our ring and multiplying by this non-zero element A. Okay, so we're going to take AX1, AX2, up through AXN. Okay, so just n products of this non-zero element A with the elements x1 through xn in our ring. Okay, now we'd like to just gather as much information as we can about this set that we have here. Okay, so the first thing we notice is that we assume that R was an integral domain, so it can't have any zero divisors. Okay, so since R has no zero divisors, what that really means is that every element in the set S has to be non-zero, okay, because after all, A is not zero, and we know that all of the xi's are not zero as well, okay, so none of the products A times xi can be zero. So S contains only non-zero elements of R. Okay, now here comes the big observation that kind of brings us home here. Okay, so could any of the elements in that set S be the same? In other words, could there be repeats in that set? Is it possible that A times xi is equal to A times xj for different I and j? It turns out that the answer to that question is no. Okay, and I want to see if I can convince you of that. Okay, so what we're claiming here is that the set S contains n distinct elements. All of them have to be different. Okay, why is that? Well, let's assume that two of the numbers on this list were the same and just see what goes wrong with that assumption. Okay, or see what results. If we had a times xi being equaling a times xj, we can do a little algebra with that. Okay, we can bring everything to one side and use distributivity to rewrite that like this. That would mean that a times xi minus xj is 0. But remember, we made the assumption that a is not 0, so if this a here is not 0, then xi minus xj has to be 0 because we're in an integral domain. We can't have 0 divisors in this ring. Okay, I'm going to remind you of that because that is a very important step here. No 0 divisors. Okay, and if xi minus xj is equal to 0, that means that xi equals xj. Okay, so what that's saying is that the only way that these two things can be equal is if the xi and the xj that we started with were equal. Okay, if you think about that, that's really proving that we must have n distinct things on this list, okay, in S. All right, well, let's put the two observations together that we just made. So we know that S has n distinct things in it, and that all of those things are non-zero. How many non-zero things did we have in our ring altogether? We had exactly n of them. They were these elements here, x1 through xn. So that means that these two lists that I'm kind of underlining in red have to be exactly the same elements. All right, so let's see if we can put that into words and add another observation to it. So we can say with confidence then that S contains all n non-zero elements of R. And since R is an integral domain, one of those non-zero elements has to be the unity element. Okay, said another way, that means that there has to exist an I such that one of those AXIs in our set S has to equal 1, the unity element. Okay, but this is a commutative ring, so if A times XI is equal to 1, that means that XI times A is also equal to 1, and notice what that says. We have just proven that A has an inverse under multiplication. The element xi is the inverse of A. Okay, so A is indeed a unit. Okay, and A was an arbitrary non-zero element in our ring, so we've just proven that every non-zero element has an inverse under multiplication. Okay, and that completes the proof that R is a field. Okay, kind of a neat little argument. There's a couple of steps there that are really kind of tricky to think of. So you might go back and read this proof again and ask yourself, one thing that might be an interesting question is, why was this an important assumption? Okay, this proof wouldn't have worked if we hadn't assumed that this was a finite ring. You might think about where we use that in our argument. Okay. Let's scroll to the next page here. There's a nice corollary to this theorem. Okay, and it says this: if P is prime, then ZP is a field. Okay, I'm not going to go through the proof of this. I'm going to ask you instead just to think about the proof and then to maybe give it a read. You'll see the proof in the written notes. It really follows from this theorem that we just proved.